look what China sent me. It's an LED driver that came with a Hengda flat panel lamp. You can buy them on Amazon. And this is actually what you get. So you might as well buy them on AliExpress or somewhere. That's the power supply. And you can see that this is the lead that goes to the LED panel, and this is the lead for the main wiring. Mains wiring is 240 volts. I bet this, multiplied by square root 2, I bet this is not rated for 300 volts over a suitable temperature range. But I guess it was soldered to those two holes. You see the one is the large one and the other one is the small one. And it's actually labeled L and N. But they decided to get with a little bit more spacing, a bit of leg stretching for that capacitor. And yeah, so you get one large hole and one small hole. And I just desoldered it. And yeah, they somehow managed to whack in that cable, because I'll be replacing it with a more appropriate one. But not sure if I actually trust this PCB at all. So you have a primary to secondary bypass cap, which should be right here, the blue one. And you can see that the trace somehow goes along there. And maybe if I find something to point. Here we go. Let's see, the isolation gap runs right underneath the transformer, which is fine. Not giving any credit to the transformer internal isolation here, but at least this looks the deal. But then you have this the small gap, so this is the smallest distance. Again, it's a couple of millimeters. It's probably going to do the trick for 1.5 or 2.5 kV isolation testing. But if you can do the leg stretch over there, might as well have just gone with it. Did it also here, and yeah. Alright, I haven't, as the saying goes, I just took it apart before turning it on. So the cap says 105 degrees C, which it needs because it's rated at 36 watts, so a few watts of dissipation are to be expected, and it's packed in this no vents plastic housing. We'll see how it goes. It's also trimmed down to the minimum bill of materials. And well, actually, that's a nice touch. See, they went with isolation slots for the rectifier, and they have an interesting star ground arrangement here, which connects to the main storage capacitor. Of course, no PFC here. Not at all. Why would you? And then this is that's a 600 volt N-channel MOSFET and some passives, and maybe underneath there is some sort of controller, or maybe they just went with an oscillator circuitry. It would be interesting to see how they actually managed to limit the current. So I'm also glad you can join me here on the inspection microscope, where we see things that we actually don't want to see. And yeah, there's our main IC. That's the only one on the board. It's a 3106 something something. It's the SOT23-5 package, and that's obviously controlling the MOSFET. It's just looking really weird. Yeah, the dead trace, I'm just figuring this out as I go. The trace that runs underneath the IC labeling, can you see this actually? Yeah, sorry, it's upside down. That's not the one that goes straight through. I can see there's a supply cap there, and yeah, let's see what we have. Obviously, it's a gate drain source. Pinout for this SVF5N60F from a brand that I cannot recognize. SCF-Cell-TM. Alright. So cell probably refers to the internal structure of the MOSFET, like the mesh feed or hex feed from, oh geez, who made this? International Rectifier? Don't quote me on that. Anyway, back to topic. You can see the source trace. runs through this couple of resistors. It's a combination of this blue one that might actually be an inductor, or it's just a neutral film resistor. And those two, one are a combined R7 and R8 resistors. So you have some current sensing there, and it just runs straight to the pin. And of course, this goes back to the star ground point of the filter capacitor with the main bypass capacitor. So, more stuff to see here, some passives. You can see R1 and R2 in combination with this electrolytic capacitor. Those two are dropper resistors, and they form the low voltage power supply for the controller IC. Not that great a solution, but usually it just needs trickle charging. And maybe this diode that we're seeing there, which goes over to one pin, yeah. You see that one trace running over there, routed through two wires. Oh, nice touch. Goes to the diode, so that will be the sustained power supply once the chip is started up. That's actually good. So it does burst start. So it charges the electrolytic capacitor and then switches over, or maybe just uses the charge that has accumulated to get the thing going, and run off an auxiliary winding of the transformer. So check. Also some isolation slots underneath the FET. That's good. And it's also a nice PCB. It's FR4, double-sided with nice stop mask and silk screen. So yeah, that's nice. Heatsink assembly, not so nice. You get what you pay for, huh? Okay, so another thing I noticed up here is you can see the diode and a capacitor. What does it say? I can't read it. I have to zoom. Yeah, it's 100 farad, 1 kV, in conjunction with those 110 kilo ohms. These four parts form an RCD snapper circuit, which is attached to the drain, so it's directly attached to the switching node of the FET. Here you can see it, hopefully. I can see through the cooling fins. And as you turn off the main switch, you have parasitic inductance, or you have distributed inductance from the traces and from the transformer that is not coupling into the secondary, and you have energy stored in that inductance, which has to be transferred or dissipated somehow. There are non-dissipative snubbers, but depending on your overall design and the currents and the inductances involved, you might just roll with 100 milliwatts of dissipation with the snubber circuit. And this clips the voltage and keeps the FET from dying. So that's a good thing. It's usually common practice to do that. So also nice. Well, R8 positioning not nice, and you can see it. You can push down on the capacitor. Maybe they just went with a large diode package because this would prevent the capacitor aluminum shell from touching the high voltage dropper resistors underneath. So yeah, we also have an input fuse rated at 3 amps. Well, I'm gonna fix that one. So output rectification, bare minimum. Interesting thing. Usually, when you have very snappy diodes or you have Schottky rectifiers, you tend to get multi-megahertz ringing as the diode current cutoff occurs. So when you just reverse the polarity and the current reverses, you get this slight dip into the negative current range because the diode conducts in the direction in which it usually is supposed to block, and then that current depletes the piece of silicon, and a space charge region forms, and that snap-off is really abrupt. So you get high frequency ringing, and usually you have a capacitor there. But not so here. whatever happened there? Oh wait, there's an RC, actually it's not populated, so they figured, why why do this? Or maybe they have different assembly options and they just figured, well, that's good enough, let's leave those two off. Apart from that, that R15 positioning's not that great in regard to C5 positioning, so they ran into some collisions there. Yeah, there's a bleeder resistor. If you run it just open, it doesn't destroy the capacitor. They also added a nice 100-volt capacitor. Not sure what voltage they're running at. Yeah, that depends on the LED configuration in the panel. So, in conclusion, it's an okay job. Not sure what to make of the isolation. The transformer also smells funky. We'll have to attach that heatsink there. Maybe, not sure what to do with that. Whack on some nice cabling, fix that capacitor, and then maybe have some nice indoor lighting. Thanks for watching.